thanks, Mart, for the nice introduction. So my name is Yi Yang from School of Interactive Computing at Georgia Institute of Technology. Today, I'm very glad here to present my work on efficiently learning and applying dense feature representation for natural language processing. I want to start from a Semantic Scholar, an interesting and super useful tool for academic researchers, which is created here at AI2. Personally, I'm also very excited about Semantic Scholar, but I'm not very happy with my own profile. So as you can see here, the number of my highly influential citations is even more than my advisor. Obviously, this is not true. So actually, the problem is that Yi Yang is a quite common name in China. So actually, multiple Yi Yang contributed to this profile. So in order to address this problem, we needed to perform a natural language processing task called name disambiguation. I have worked on a similar task called Twitter entity linking. So given a tweet like this, entity linking aims at detecting all the mentions in this tweet and linking them to corresponding Wikipedia pages. So similar to named disambiguation, here we also need to disambiguate different named entities with respect to a mention in the tweet. So as I will show later, effectively utilizing sort of dense feature representation is very crucial for this task. Actually, much of my work has been focused on non-standard languages, such as the social medium text and the historical text. Over the past few decades, NLP researchers have been working very, very hard to improve many core NLP problems. On news text, the current state-of-the-art NLP system can achieve reasonably good performances, as you can see here. But when it comes to tweets, several studies suggest that the performances of these NLP systems experience dramatic drops. So what's going wrong here? What's the problem? It turns out the current NLP systems are very brittle due to two main reasons. First, they are usually trained on some standard news text, so they are vulnerable to the variation of non-standard languages. On the other hand, obtaining annotations for non-standard languages is non-trivial. It's often time-consuming and expensive. The second reason is that most of these NLP systems employ high-dimensional sparse features like backward words. These sparse features are very powerful and expressive, but they also make the systems easy to overfit the standard training dataset. Let's take a look at this tweet, which is not as lovely as the previous one. Here you can see there are actually several non-standard tokens in this tweet. So under the backward words representation, the semantically related words your is actually totally different from you are. So people realize this problem and start to employ more and more dense features. Actually, my thesis topic is about building robust NLP systems with these dense features. But two challenges still remain with these dense features. First, it's not very easy to learn them. So currently, most NLP systems simply utilize some pre-trained generic word embeddings and fail to leverage some task-specific information. And it's also very hard to work with them. The reason is that the traditional linear NLP models are often not expressive to capture the nonlinear relationships between dense features. So in the talk, I will show you how to address these two challenges. In the first part, I will talk about efficiently learning novel dense feature representations by exploring some task-specific information and text metadata attributes. In the second part, I will present novel tree-based nonlinear models, which are good at capturing the nonlinear relationship between features. All right, this is the outline. I will talk about our unsupervised domain adaptation algorithms, feature embedding, which is dense feature representation learning method. And then I will present our tree-based nonlinear structured learning method called S-MART. And I will show you some result by applying S-MART on the Twitter and the LinkedIn task. Finally, I will discuss some future work. All right, let's just dive into the first part. So domain adaptation is actually a very important problem for natural language processing, and it can help to improve standard NLP systems on processing non-standard languages. But again, this problem is very challenging because source and the target domains are usually with different data distributions, so it's very hard to estimate the desired conditional probability py given x target using py given x source. So the solution is that we can try to learn some sort of joint feature representations PZ by leveraging some feature co-occurrence statistics, so that under these new feature representations, some target instances will be more similar to source instances. I will use the well-known sentiment analysis as an example here. Assume our source and target domains are book reviews and DVD reviews. So the first thing is that we can split the feature space into two parts. The cross-domain features are shared by both domains, but domain-specific features only appear in one domain. So if we simply train our sentiment classifier using backward representation, all of these domain-specific features will be useless. But we still want to make use of these valuable domain-specific features. How can we achieve that? It turns out we can leverage some the feature co-occurrence statistics. And the basic idea here is that we may have observed some word pairs like good or best-selling and bad and broken tend to co-occur with each other. Then we may think maybe these features are actually similar to each other. So the simplest way to incorporate this information is that we can do some sort of normalization of this feature co-occurrence count and adding them back to the sentiment classifier. And it turns out this simple method actually improves the task a lot. Okay, we can actually adopt this similar idea to many other core NLP problems. So many NLP tasks need to predefine a list of feature templates to. All right, question.
Sorry, can you go back to the previous slide?
Sure. Sorry. Okay.
Yeah. So sorry, this went by a little bit fast. So once you note that best-selling and good co-occur 8 times in your
training data. Yeah.
What do you use that as an additional feature? How do you? What do you do with that information?
Yeah. So here the other is that here we have, so since good is a cross-domain feature and best-selling is a source domain specific feature. So but maybe in our targeted dataset we also observed some other target specific features also tend to co-occur with good. Then we might think best-selling will be similar to the target specific features which also co-occur with good. So the simplest way to leverage this information is that we can do some sort of feature, sort of normalization on the count. Like if best-selling, so like I think the simplest way is that we count the total number of feature co-occurrence count, and we can divide this number 8 and 6 by the total number and treat that as new features. So if there are some other targeted specific feature also have a high value with respect to the same cross-domain features, then we can use that value as new features.
So let me repeat what you said just to make sure I understood. So
sure.
You take the co-occurrence statistic between good and best-selling, you normalize it by the total count, so you get a percentage, and then you use that percentage value as a new feature to describe a new feature of all examples of how do you use the new feature?
Oh yeah, so actually, we will merge the source domain data and the target domain data together, and we will compute the feature called occurrence count based on the merged data set. Since computing this count do not require any label, so we are able to do that. Then, then the information on the source side will be connected with some other some feature called occurrence information in the target side. So we are able to link them together. Actually, that's the best idea. Yeah. All right. So I will go to this slide again. All right. So for many NLP tasks like path retagging, NER, and trunking, we need to predefine a list of feature templates in order to extract the features. For example, assume you want to tag some text, and the feature templates may be the current token, the previous token, the next token, so on and so forth. And the corresponding feature indexes and the feature values are also shown in this table. So these feature templates are actually very good because they encoded some task-specific information, which are our human prior knowledge. But they are also very bad under this domain adaptation setting because they lead to extremely sparse features. So we address this issue by, again, trying to transform the sparse features into some dense feature representation. And in our NACO paper, we proposed a method called feature embedding. So here the idea is that we can try to directly utilize the feature co-occurrence statistics to induce low-dimensional neural feature embeddings. So the basic idea will be very similar to how we train the word embedding. So in the grammar method for training word embedding, we need to use the current word to predict the surrounding word. So here we need to use the current feature to predict all the other features that also in the same instances. So here you can see we can use the feature here to predict all the other features here. So, so I think different from how we train word embedding is that since we here trying to exploring some task-specific information encoded in the feature templates, so our feature embedding may be able to perform better than word embedding for some specific downstream applications. All right, so the resulting feature embeddings will have the property, say, if you have one source domain specific feature, one target domain specific features, and you found that they both tend to co-occur with the same cross-domain features, then actually these two domain-specific features will be close to each other in the feature embedding space. Then you can put this feature embedding as new features. Then we'll have the augmented new feature representation, with, which is a simple concatenation of the original features plus these feature embedding features. All right. So much prior work on unsupervised domain adaptation for natural language processing are this kind of pivot-based approach. So the key idea for pivot-based approach is that we need to first explicitly select a small number of cross-domain pivot features. Like for sentiment classification, some pivot features may be good, bad. And then we will need to learn some projection metrics by reconstructing or prediction all of the pivots using all the other features. But these pivot features have two main drawbacks. So actually our feature embedding approach improve upon these two drawbacks, which we can see from the experiments. So here in our experiments, we will train our path-rich tagger on the standard Wall Street Journal news text and test on some web text like reviews, emails, blogs. And our no adaptation baseline is able to obtain 89.9 accuracy. two prior unsupervised domain adaptation method can achieve some improvements over the adaptation baseline by 0.5 to 0.8 accuracies. Finally, our feature embedding method significantly outperforms all the baselines by more than 1 point of accuracy. All right, so do we have more questions regarding the work here? Great. So I think another weakness for prior work on unsupervised domain adaptation is that they only assume we need to work with two domains. One is the source domain, one is target domain. But in the real world, we may have some situations that we do have a set of related domains to the source domain or target domain. For example, assume we want to perform parsing tagging on historical text like 16th century dissertation, and our source domain is 19th century narrative. The question is that whether we can leverage all of these intermediate domains to further boost the results. So formally, we proposed a new task called unsupervised multi-domain adaptation. The goal of this task is that we want to leverage some domain attributes like general tempo epicals to further improve domain adaptation task. Okay, so the method we take here is very simple. It's a simple extension of our feature embedding method. So here we assume for each feature we will have several versions of feature embeddings. Each version of feature embedding corresponds to a specific domain attribute, and we further assume a domain-independent version of feature embeddings were shared by all the domains. So by doing this, we are actually encouraging all the domain-neutral information go to the domain-independent version of feature embeddings, so that we can use these feature embeddings for domain adaptation. Okay, we verify this multi-domain multi-feature embedding earlier on another path-specific tagging task. Here we perform path-specific tagging on historical Portuguese text. Again, our no adaptation baseline is able to achieve 87.5 accuracy, and two prior unsupervised domain adaptation method is able to obtain about a 1 point improvement. Here, our single feature embedding method is already able to significantly improve the result by like 1.5. Our question. We did not do the test, but I think that should be the case. But usually for some tasks like path-specific tagging, some improvements like 1 point will be some very good results. So the current paper on some path-specific tagging on English task, if you are able to achieve like 0.1 to 0.2 improvement, that will be quite good.
Yes, depends on how big this corpus is.
Yeah, sure, yeah. Yeah, so the size of this corpus include 3 million tokens. So yeah, so our training set, since we split the entire dataset into several domains, so our training set contain the number of tokens like 200 to 300,000, I believe, yeah.
What kind of tests would you perform to confirm?
Oh, yeah, so our setting is this. So we will train our tagger on this part of this entire corpus, and we will test on all of this data set. So we
Sorry, I meant like statistical testing.
oh, I see. All right, sorry. So I think for the statistical test, we will be able to compute the p-value or something like that, but we did not do that. Yeah. Okay, finally, our multiple feature embedding earlier is able to further boost the performance over single feature embedding by 0.4 accuracy. Okay, that's the first part of my talk. So do you have more questions about this part of work?
I just was wondering, you talked about the size of the training set. How about the size of the test set?
Okay, so the size of the test set, so we have two settings. So we split this entire corpus into six domains. And we have two settings. In the first setting, we will use the first domain as a training dataset, as the remaining 5 domains as a test dataset. In the second setting, we will use the first 2 domains as the training dataset, and the remaining 4 domains as the test dataset. So the total number of tokens in these 6 domains are similar to each other. Yeah, so it's like in total there are 3 million tokens. So in each of these domains will be 500,000 tokens or something like that, I think.
So it sounds like in the minimal case, the test set will contain millions of tokens?
Yeah.
And so the results are showing these percent or 2% differences on millions of examples.
Yeah. So actually here we take the average of all the test set. So we will use the first domain as a training data set and the remaining 5 as the test set. And we will take the average of the 5 results for the 5 test sets. So actually the result reflects like 2.5 million tokens. All right. Okay, so in the first part, I will demonstrate you how to learn better dense feature representations. In the second part, we'll talk about how to better work with them. So some traditional NLP systems like to use linear models because they already exploring this sort of expressive sparse features. So some linear models like linear SVM and maximum entropy are usually sufficient enough to achieve very good results. But this setting is challenged by dense features because linear models are not able to capture the complex nonlinear relationship between dense features. And people start to work with more and more nonlinear models. So I think the resurgence of neural networks is certainly part of the story. But we also have another great class of nonlinear models, which are tree-based models. We have seen some empirical success of this tree-based method on various areas like information retrieval and computer vision. And these tree-based models do have several advantages over other nonlinear models, like they can handle categorical data and count categorical features and count data better, and they are actually implicitly performing feature selection. So this property makes the tree-based model a good fit for our target application, Twitter anti-Lincoln. Due to the lack of training dataset, people usually employ a small number of dense features, some statistic-based dense features for this task, like the view count of a specific Wikipedia page and the cosine similarity between a Wikipedia page and a tweet. So tree-based model turns out are very good at handling these types of features. Unfortunately, we are not able to adopt existing classification-based tree-based model for this task because this task is actually a structured learning problem. We can see this point from this tweet again. So given the tweet, our system will treat all the n-grams in the tweet as possible mention content. So there will be a lot of overlapped mention contents. Like if you want to link the correct mention content Eli Manning to the corresponding Wikipedia page, you need to first link both Eli and Manning to the new entity. And the same cases for New York Giants and the word theories. All right, so structured learning is conceptually different from binary classification, because here we need to model a joint scoring function as x and y over an input structure and an output structure rather than a simple function of x. And in order to obtain the prediction, we often need to perform some sort of dynamic programming inference, like Viterbi. So here in our SR paper, we proposed a novel class of tree-based structured learning method called structured multiple additive regression trees, S-MART. So since there are actually the full search space for output structure is exponentially large, so we first assume a decomposition of the scoring function over several factor scoring function, so S equals to a sum of F. And the key point here is that we choose to directly optimize the factor scoring function using a technique called functional gradient descent. So here, the G here is called the functional gradients. Another key point is that we will use a regression tree H to model the functional gradient G. Then our model will be a nonlinear model and is able to capture nonlinear relationships between features. Okay, let's take a close look at how the functional gradient descent works. So we will need to optimize F. So we will first initialize F equals to 0, and assume in the m-1 iteration, the function F looks like this. We will need to compute the functional gradient using this equation. And note here, since we are doing structured learning, computing the functional gradient actually require several different inference algorithms with respect to different loss functions and structures. The next step is very simple. We just add up the previous function with the negative functional gradient together. So the question here is that how we model this functional gradient. Because it's a function, we might need infinity number of data points to model the function. Here, SMART address this difficulty by first compute several point-wise functional gradients by go over all the training data points. And then we will choose to use a regression model to approximate the functional gradients using the point-wise functional gradients. In particular, we use the regression tree model, which is a nonlinear model due to the nonlinearization boundary. And then we are ready to apply SMART to our Twitter anti-linking task. So the first step, we need to write down a specific loss function. We have considered both log loss and handling loss, but we found log loss perform better than handling loss for the task. And then we can compute the point-wise gradient using this equation where the conditional probability requires non-overlapping inference. Okay, we adopted the two. So before I go into the evaluation, do you have questions for the method? All right.
So which part in the SMART is different from the original gradient table?
Yeah. So here we can see from this equation. So here the loss function also involves in y, but in the original gradient GBDT model, the loss were only involved in x. So here we can see there are two y's here. The first y is that in order to define the loss the scoring function s, we need to consider y. Second, in order to define the loss function, we also need to consider y.
What's the difference between y star and y star?
Sorry.
What's the difference between those two y's? They're both missing.
All right, so the y star is the good label. So it's a good output structure for the tweet, and the yk is the model, is one possible model prediction for the k factor in our case. All right. Okay, so here in the experiments, sorry, go through this. Okay, so in the evaluation, we considered two evaluation policies. So the RE-driven evaluation is very similar to the standard evaluation for NER, and the R-driven evaluation focuses more on the entity disambiguation aspect of this task. So given a query entity, our system needed to decide whether the tweet is relevant to the query entity or not. So let's take a look at the results. So the previous start of the art system for this task is based on linear structure SVM, which is able to achieve 17.3 accuracy. And the non-linear version of SSVM is able to improve 1.4 point of F1. Interestingly, we found that the non-structured tree-based model MART is already to beat these two structured SVM models by a large margin. Finally, by incorporating the structured information, our SMART method again significantly outperforms all the alternative baselines for the RE-driven evaluation. And the result.
Sorry, before you continue.
Sure.
The improvements here, are they due to improvements in precision or improvements in recall?
Oh, yeah. So here we do a sort of a balance between precision and recall.
Right,
so
that's what the F measure does.
Yeah.
If you look at the curve, the precision recall curve, how would you characterize where the
yeah. So here, what we did is that for each of these system, we will attenuate the F1 score based on the data set. So we have some way trying to improve or decrease recall of each of this system. So for each of these system, actually we already are trying to achieve the best F1 score. So actually our SMART model improve upon all of these systems in terms of both precision and recall. Okay, so the results on R-driven evaluation are actually very similar to that for the RE-driven evaluation. We can see again our tree-based structured learning method SMART improve over the three baselines by like 3 points of F1. Okay. So in the future work, first I think we can try to incorporate some social relations into this Twitter and the Lincoln task. So here the idea is that socially connected user on Twitter may be interested in similar named entities. And I think the similar idea can be also applied on Semantic Scholar, because if there are two researchers co-author a lot of papers, they may have the same affiliation. In terms of the model, we can try to jointly modeling information entity and the user using some low-dimensional vector feature representations. And assuming we can perform very good result on the Twitter on the anti-linking task, actually then we are able to link the unstructured text with the structured knowledge base. So we are actually bringing valuable contextual information from the knowledge base to the unstructured text then we can have some sort of more accurate user profiling, which will help to improve several downstream applications like query understanding and contact recommendation. Okay, so that's all, I think. So hopefully in the talk, I will convince you that this dense feature representation are hot, popular, and also very useful in NLP systems. And in the talk, I'm first talk about how to learn better dense feature representations by leveraging some task-specific information. And then I also present a novel tree-based nonlinear structured learning method to better work with these dense feature representations. And I think that's all for my talk. Thank you.